Okay, in this video I'm gonna talk about DeepSeek, and also we're gonna find out how DeepSeek thoroughly works from the math foundation up until the code itself. And for the coding, I'm not gonna write the code itself, but what I try to do is technically walk you through the code and try to run it. And the way that we're going to do it is that we're going to take a base model just like the one that they do it in DeepSeek R1 paper. We're going to take a base model and we try to do a kind of aligning with reinforcement learning and trying to make a kind of R1 version from that base model. So yeah, that's how this video is gonna work. And also, before going to the DeepSeek, in fact, paper, what I'm trying to do is I will try to first explain a little bit about different types of reinforcement learning, human assisted human feedback methods, that how aligning LLMs work, and then we will go, and that would be a good foundation to understand that how DeepSeek itself works and how they manage to make DeepSeek so optimized. So yeah, let's just start it. So the first thing that I want to start with is aligning large language models. So what that aligning means. So the thing is, when we try to first to make a large language model, we do a kind of training or pre-training, whatever it's called. And the thing is, when we do that, it's not necessarily 100% accurate. For example, when we train something, I don't know, a big model, a big LLM, it might be, when we try to talk to that model, it might be harmful, or I don't know, it might not give, in fact, answers in a proper chat format, or might be, as I said, sexist, or I don't know, racist, harmful, so on and so forth. So what we need to do in order to put it into a right framework, we need to align it, and that's what is it called, aligning large language models. But how it is possible? So the most common framework for this is reinforcement learning from human feedback, RLHF, which we try to kind of teach the model from human feedback or human preference, that what is the best way to, for example, answer a specific question, or what is the framework that you need to work on it, something like that. So yeah, as I said, the supervised fine-tuning is just a pre-trained LLM first got taught to mimic human written examples. You can see it kind of like LLM trying to understand grammar or structure of the I don't know, text or language, so on and so forth. But when we do the reward modeling or human feedback, so what happens is humans are asked to rank different model responses to the same prompt. So this would give a kind of preference data. So imagine if we have, let's say we have a prompt and we can call it X. So we can have a couple of different responses for that. And let's call the one that we prefer as YW, or winning answer, and the one that we do not prefer is the YL, or the losing one. So the response YW is preferred over YL. So this is used to train a separate model, a kind of reward model with usually reinforcement learning, and we will find that sometimes we don't need it necessarily. We don't necessarily need to use reinforcement learning, for example, in a method like DPO. And then once we have the reward model, it kind of learns to score responses. on, for example, how much a human would like them, or what's the preference for a human. And then we have as I mentioned, reinforcement learning, fine-tuning. So let's just quickly jump into the classic approach, which I think the paper is for 2017 or 18, which the method is called PPO, or Proximal Policy Optimization. Okay, but what this PPO means and what it says. Okay, first let's just try to understand a couple of mathematical foundations and about policy gradient methods, so on and so forth. And the thing is, these sections, some parts of this section uses reinforcement learning, which I'm not gonna explain it in full detail here. So what I assume from you is you are familiar with some concepts from reinforcement learning. And if you're not, what I can suggest you is there are a couple of tutorials on YouTube. One of them is, for example, from I think David Silver. I think I can put it. I will put the link in the description, so you can go and have a look at it and then come back and see if you can understand it. So I'm not gonna go into the details of the. I'm not gonna, in fact, teach or explain anything about reinforcement learning, but I will explain how we use reinforcement learning in this LLM aligning. So I assume that you know reinforcement learning. So yes, let's go back to policy gradient theorem, the foundation of learning. So the big picture. So what is the big picture, or kind of analogy for that? Just imagine teaching a student to write an essay, or improve them when they write essay. When they write something good, you try to encourage them to go into that direction or repeat that method or whatever that, or that style more and more. And when they write something useless or bad, you try to discourage them. So that's exactly what policy gradient tries to do for LLMs and generally in reinforcement learning. So what we have here is technically, if I can zoom in, so imagine we have the policy, and in the policy we have the actions taken in a specific state that we are. So if we are happy with that, we can have a kind of something called what's that? Let's say a choice, a kind of choice threshold, that if we're happy we can give more reward, or giving a more reward towards that to encourage the model. If not, we can put something negative and discourage the model from doing that. A kind of analogy for this equation would be, just imagine theta is model's brain, billions of parameters which we're trying to kind of optimize them. The gradient, which you might have guessed, that is the direction that we're trying to adjust the brain, or the direction that we're trying to move towards to. The policy of theta is how likely is the model to choose an action given a context like ST. And the log version of it, it's just a kind of mathematical trick in order to make the calculation easier and make it more stable. So the advantage is something that if the choice is if the choice is a good choice, we can give a good positive advantage in order to encourage it. If not, or if it is worse, we can give something negative than the average response. So that's how technically works. For example, an example for advantage. We're gonna go further into details, so this is just a quick high overview of advantage and all those. We will go much more deeper in a minute. So for example, for the advantage, just think of it, if advantage is something like +2, what it means that this token choice was really good. Make it 2x more likely next time. So I'm very happy with the essay that you write. Keep the same way, keep the same style, and write it in that way, something like that. Or if it is 0, so I don't have any preference, for example, just do as you do and don't change anything. But if it is negative, so that was, for example, I don't know, a grammatical error or dictation error, something like that, try to avoid it next time. So that would be a kind of analogy for it. And just a quick example again, which is very, as I said, high overview. Just imagine a scenario that we have ChatGPT and try to train it to better understand the physics explanation. So the user prompt would be something like explain quantum physics to a beginner. The current context is quantum physics is, and the next token of choice could be fascinating. Quantum physics is fascinating, or quantum physics is complicated. And imagine our policy, the current policy probabilities is given the context or the prompt and the current context, the possibility or probability of fascinating is 70% and complicated is 30%. So, and imagine at the same time we have a human feedback analyzer or analysis which says, for example, for the fascinating, human rating would be 4.5 out of 5, and the advantage would be something around 2.3. And these are the made up numbers. These are not based on calculation. This is just for the sake of, in fact, demonstrating that what these could mean. So once we calculate the policy gradient, so this would be the result. So the loss would be minus 0.82. And imagine the gradients push the model to increase that the choose of fascinating from 70% to 75. So what model learns is, when explaining complex topic, use engaging language, and that's how we align it generally. So let's jump into the next in fact section of it. So this section is in fact continuing the previous one, which we say Trust Region Policy Optimization, TRPO. So what it generally says, so we understand that how we, just in a very high overview in the previous section, we understand that, okay, how it works and how we can give guidance to a model based on its policy and human feedback and those advantage factors, so on and so forth. But the point is by how much we can and we should give direction to the LLM. So that's very important. So we have something called catastrophic problem, which states, imagine you're learning to drive and you make a huge steering correction. So what happens? You're gonna crash. Similarly, if we do the same thing to LLMs, if we do a quick shift or quick jump in gradient or alignment or feedback, so what will happen to the brain of LLM? It might forget how to speak English. It might not necessarily be this big, but it might forget a specific amount of knowledge that has been learned from the previous steps, which is definitely something that we want to avoid. So how we can overcome that and how we can do it. So the main objective, what we want to maximize. So what we want to maximize is, imagine that now we have two policies. One policy is the old policy, which technically means the base LLM, and the new policy, which is the LLM that we want to be good in a certain direction. For example, be good at chatting, like ChatGPT. So let's quickly decode this equation. So as I said, the policy, the new model's probability of chosen token, AT, the old policy, old model's probability of choosing the same token. The ratio is how much more or less likely this choice should be or is going to be. The ratio, for example, if the ratio is 2, the new model is 2x more likely to choose a specific token. If it is 0.5, the new model is half as likely to choose this token. Or if it is 1, it's technically they are the same. So they are the same in terms of probability of choosing a specific token. And by the way, I might have forgot to, if I want to explain what in the world of LLMs, what A and S means. So imagine that we generated a text. Imagine, for example, I'm asking, how are you, from the LLM. So that how are you is the state, and the next token would be the action that we're taking. And imagine it says I, so it tries to say I'm good. So the I would be the next generation. So which we, in fact, in terms of reinforcement learning, we choose the word A or the action A from the probabilities or logits of the LLM. Now the next state would be how are you, question mark, and then I. And what's the next action that we're going to take? Would be am, and so on and so forth. So that's technically how it works in the world of LLMs. So, okay, up until here, we understand that, okay, we have this ratio. So what this logic of the advantage means. So again, just the same as before, if it is positive, it's a good choice. We want a ratio bigger than 1. If it's negative, it's a bad choice, so we try to discourage it. Once we have all these, now again, remember what was the problem? We have the catastrophic problem. We don't want to do a huge string correction, or we don't want to do a complete sudden shift. So how we can do that? Remember that all LLMs at the end of the day, or neural networks, are probabilistic models or distributions. So what I'm trying to do here is I want to change my new model to a certain direction, but I don't want it to change too much. And at the same time, both of them are probability distribution. So in mathematics, we have something called Kullback-Leibler distance, which technically tries to estimate the distance between two probability distributions. So that's exactly what we use here. So we can put this Kullback-Leibler here and say that, okay, I have this old policy and I have the new policy which I'm trying to get to and make the LLM better. If I don't want to do a sudden change, so what I would try to do is that, okay, I would try to teach my LLM to go in specific directions, try to give it advantage and reward, so on and so forth. But at the same time, with this Kullback-Leibler, I will limit it from huge jumps. So I would say, okay, the distance from the old policy should be less than, I don't know, a specific amount, a delta number. So what Kullback-Leibler of 0 means? It means the new model thinks exactly the same as the old model. Why? Because both of the distributions are the same. If it is 0.01, they are very similar, just tiny differences. For the first one equals 0, they would be identical twins. In the second one, they are kind of siblings. If the Kullback-Leibler difference is 0.1, noticeably different, but still related, like cousins. And if it is something like 1, they are very different. They have different thinking and reasoning. So they are technically the strangers. So the constraint says you can, technically what it says is you can improve the model, but don't let it become too different from what it was. So keep the distance less than a specific amount. So this is a really good concept, but it has its own problems. So what are those problems? Why is it hard? This creates complex optimization problem, first of all. The second of all, it has a second order derivative, and also it is really hard, it's really, complex and expensive to calculate. So, and also there's an example here, which I'm not gonna go through with, but if you like, I put, so you can just navigate to this URL, and I put it put the link into the description, and you can just go and have a look at it. So remember that we have the ratio, and we try to say that, okay, if we have this specific, do not try to diverge too much from the base model. But the thing is, imagine that we have an example which in that case, model tries to learn something new, tries to align itself in a specific manner, in a specific way, and that data and learning is important, but because the jump is high, so what happens here in Kovac-Libler is that I'm gonna reject that update because it's too big, but also at the same time what happens is I'm gonna lose that update because it was too big, but at the same time it was very useful. So what can I do? So there is something very smart that we can do, which is the core idea of PPO, Proximal Policy Optimization, which we will learn it in a minute. So what's the PPO's brilliant solution? So it is something called clipping. But what is clipping? So what if instead of complex math constraints, we just put a simple speed limit into that? So what it says, okay, just remember this ratio again. So we have ratio 1 means, again, no change, 1.5. New model is 50% more likely to choose this token. 0.7, 30% means 30% less likely to choose. 3 means dangerous. The model is 3 times more likely to choose something. It's too big, too much. Or 0.1, again, is too dangerous. So what PPO does is it uses a concept called clipping. So as you can see from here in this equation, it means that, okay, I'm gonna calculate the ratio and the advantage multiplied to that ratio, but at the same time, so imagine that the update is about, I don't know, 2% or 2 or whatever that it is. I would say, okay, limited by this amount, limited by epsilon, 1 minus epsilon or 1 plus epsilon times advantage. So let's quickly go to the example so you can understand it better. So what it technically means, it means that you can go in that direction, and I will allow you to update because I don't want to lose that useful update, but because it was too much, you're not gonna go too far. Just imagine when a kid plays in a street or something, what usually moms say. They say, stay close. You can play, but stay close. So that's exactly what happens. So if epsilon is something around, let's say 0.2, we clip the clip ratio would be something 1 minus the epsilon and 1 plus epsilon, which would be 0.8 and 1.2. So if the ratio is 5, so if we clip it, so as you can see, it is too low, so we bring it up. So when we do this minimum, in fact, we put it into this minimum function. So this is the it is the what's that? 0.5, 0.8, 1.2. 0.5 is less than 0.8. So bring it up to this minimum, which is 0.8. So it says that, okay, I didn't like your essay. It was too bad. So I'm not gonna say totally forget it. I'm gonna say try not to use it that much. So that's how the update technically will happen. And the same for 2.5. It is too much. Don't repeat it too much. Don't be, I don't know, greedy into that. Imagine that you're writing an essay about a specific thing, and imagine the example that you use, mainly people use for LLMs, is when I want to say LLM to be polite, they can just repeat polite words, just for example, thank you, or something like that. They can just repeat it, and it is polite, but it is useless. So what I can say is, it can say, yeah, it was good, but don't repeat it too much. So I will clip it, as you can see here. So the main operation, PPO safety net. We compute two objectives, one with the original ratio, one with the clipped ratio. Then we take the minimum, we take the technically minimum of those two. And why this works and why it works fine and is useful. If the model wants to make a good change, positive change, clipping prevents it from getting too excited. Or if model wants to avoid a mistake, a bad change, again it will clip it from making huge destructive changes. The result, it's a steady, stable, and learning without catastrophic failures. So that's what technically will happen. And again, there is a numerical example for that, which we can quickly go into that. The scenario, just again, training ChatGPT to give a better programming advice. So the user question is, how do I learn programming? How can I learn it effectively? So the context generated so far is the best way to learn programming is, and the next token decision is practice or reading. So technically practice could be a better choice. So in PPO setting, imagine that we put epsilon to 0.2. So the clipping range would be 0.8 and 1.2. The case one, high reward token, practice focused response. And imagine the complete response would be, the best way to learn programming is practice, build projects, solve coding challenges, and write code daily, so on and so forth. So human feedback would be very useful, actionable advice, and perfect. So advantages, 1.8, much better than average. The old policy is 30% chance, and imagine the new policy would be 65% chance. If we calculate the ratio, just this one over here, so that would be, the ratio would be 1.625, which means 62% increase. And 62% is too much. We do it and we give it to this clipping function, and we say that, okay, don't get too excited, just make something which makes sense. So we clip it, and now it is just capped at 20% increase. The final objective would be 2.16. And imagine the same result for the reading focus, which is the failure. So that can happen for that example as well, which you can read it through and go through it through the example. I'm gonna skip this one. You can have a look at it. It's not very in fact important, this section. Yeah, I can just quickly go, let's go through this part. PPO's triple optimizations, juggling 3 goals. So imagine training a student who must give a better answers, predict test scores accurately, and stay creative at the same time. So what happens in this PPO's triple optimization is all those 3 should happen at the same time. So we have the loss of the clip, loss of the value function, and also the state and policy. So the goal 1, better token choice, policy loss. So what it says, it makes the model choice better to choose better words and tokens. This is technically the clip objective that we learned about just a minute ago. And the next one, the second goal, is better predictions, the value function. The value function is like a fortune teller, that it tries to predict that what's the possibility or probability of the next token to be chosen. So V of phi for state T is, what that means is I predict this response will get a reward of 2.3. That's what we're trying to make and teach in that and learn technically in PPO. And what the target is, we have a target. Actually, it got a reward of 2.8, and we try to make a kind of value function to make sure that we can predict the reward of the choosing a specific token for that LLM. And why we need this? Good predictions, better advantage estimates, and better learning, technically. And stay creative. So why we need to stay creative and to having a kind of entropy, higher entropy, because we know that if we don't have that creativity in LLM, so it can be greedy and it can be sometimes defeat the whole point of the LLMs being an LLM. Sometimes we don't need it. So for example, imagine that you want to, I don't know, extract entities and put them into Pydantic output parser. So technically what you need to do is you need precision there. So you don't want it to be creative, you want it to be accurate. But sometimes you want to, for example, when you want to write an essay or write code, something like that, sometimes you need it to be creative. So that's why we need this creativity here. And I think this one is somehow, again, there was an example which you can go through with. I don't think we need this part. Again, if you want to further understand it, you can go through it by yourself. And just let me see if I need more explanation about that value function, or maybe I can explain it in the next section. Just give me a second. So yeah, I think I'd better to explain this value function here. So remember when I said about this value function, no, it was, yeah, right here. So the value function is like a fortune teller. So what that means and how we can make that value function, because imagine that we're trying to generate the next token. So how can I put a value function on that to estimate or predict what is the value of the, I don't know, reward or human preference is going to be. So there is a kind of good method for that. So what is that value function? First of all, the value function v of x or v of x given y estimates expected reward that a language model will receive for generating a particular response to a prompt. So that's how technically it happens. It's mainly using, as we saw in PPO, but where it comes from and how we calculate it. So remember, when we want to generate a token in large language models, we give it to that transformers layers, and those transformers layers, we have the hidden states, and those hidden states, they just work and output the next token after the feed forward layer. So what we do here, instead of having that feed forward layer, what we can do is we can technically just put a linear layer and use the hidden states in order to calculate just the probability or kind of value of those tokens, the tokens that are going to be generated. So instead of feed forward, which would give us a kind of choice between different tokens and that softmax and so on and so forth, what we do is we literally put a hidden layer and we try to estimate the value function, and we try to minimize the loss. So if I can go here, so yeah, so where it comes from, after a transformer process, the input sequence prompt process response, it produces hidden states vector, which is technically in the shape of batch size, sequence length, and hidden size. And let's say these are the specifications of those numbers. So the hidden state is a tensor of, let's say, 1, 10, 7, 6, 8 for, let's say, case of the GPT-2 is small. What's the value function and how it works is just, again, don't forget it's the expected reward model would receive for a given prompt or prompt response pair. So the way that it will be calculated is, if I can, yeah, it's just simply a learnable linear layer that maps to hidden states, to a scalar. So it's just simply WT, the weights to the hidden states, and plus a bias. Let's say the weights are something like this and bias is something like this. If we want to calculate the V or the value function, it would be something like 2.1. This technically would be just the way that it's going to be calculated. And we try to minimize the loss based on the human preference, because humans are technically trying to give the value to the response. And yeah, and I think that's done. And again, I will put this PDF also on my GitHub. You can go and have a look if you wanted. And yeah, and the loss function, as I said, it's just technically the value function over the reward that a human would or might give to that pair of the response and action. So the next section, what I'm trying to do is I will try to go through the DPO. So this was the PPO. Then we have the DPO, which is the direct preference optimization or difference, maybe. Let me double check it if I'm direct preference optimization. Yeah. And how the direct preference optimization work technically. Just let's quickly recap what we understand. So SFT, supervised fine-tuning, creates a solid foundation by teaching the model good examples. Reward modeling learns human preference from comparative rankings. PPO, what PPO tries to do, optimize the policy to maximize rewards while staying stable. And why this works? Because at each stage builds on the previous one, creating a robust alignment pipeline that scales human feedback effectively technically. And just some implementation notes, the data required, because it's, imagine it's a language model and we're trying to make it more polite, or I don't know, make it to be better at coding, so on and so forth. So it requires lots of data. Technically something definitely above 10k of examples or even more. So something around 1 million examples or pairs would be perfect. And computational cost, it's really expensive, because remember that we had two models. We had the base model and the new model, which we have to train them at the same time. So we do that inference and training at the same time from two models, which is really expensive. So base policy, old policy, and the new policy, which is really expensive. And yeah, that's technically for proximal preference optimization. Okay, now let's go to the second part, which is DPO, or Direct Preference Optimization. So as we saw in PPO, so we need to make a kind of reward function, and also we need to make the value function from with reinforcement learning, which could be kind of expensive and a little bit problematic. But is there any other way that we can do this in a better way, or maybe less computation? So the thing is, based on what we know, in fact, the human nature. So imagine that we have a couple of LLM generated answers, or a data set that we want to teach to LLM or align LLM. So what is hard? The hard part is if we want to score them. So for example, imagine that we have 10 responses for a question and we want to score them. So the problem is each person has its own kind of point of view and, judgment. So they might score it in a different way, which makes things a little bit tricky and problematic. And also, at the same time, the value function and reward function that we want to train. But the thing is, most of the time, humans are much better in comparison. So imagine if we have two possible answers, it's hard to find, a group of people who agree on the same scoring for each of the pairs of answers, but it's much easier to tell them, okay, just compare them, which is better than which one. So many of them would say, for example, A is better than B, but when we want to score them, one might say a score of A is 3, the other one might say a score of A is 4, so on and so forth. But comparison wise, it is much easier that they can reach a much better kind of common answer. So that's technically what Direct Preference Optimization, or DPO, is all about. So as we saw on PPO, so we had reference data, we had training reward model, RL fine tuning, and then align LLM. So the thing is, on DPO, we totally get rid of the reward model. What we do is directly optimize policy via DPO loss, and we will see that in a minute, that what that means and what it is. So yeah, let's jump into it. So about DPO, so what is the mathematical concept of it? So mathematically speaking, so what we want to try to do technically is eliminating the reward model. Okay, but what that means and how we can do it. So step 1 is optimal policy formula. So what is the optimal policy formula? For any reward function like R, the optimal policy to maximize the RLHF objective has this exact formatting. The policy of R and the answer y given a context x is 1 over z of x, and this z of x, just remember this, I will go in a minute deeply into it and what that means. 1 over z times the reference policy times exponential of the 1 over beta of reward function, which, as I said, pi of r is the optimal policy, the reference policy, pi ref, exponential, this exponential is exponential of the scaled reward, and z of x, normalization constant, which ensures the probabilities sum to 1, which is the problematic part. So let's see what this z of x is and how we can technically get rid of it. But first, let's just quickly finish this and then we can go back to that z of x. So what we can do if we just solve this equation for the reward function. So this is technically how we get the in fact the equation back. And imagine again from the PPO side, we had two kind of answers, the winning answer and the losing answer. So imagine now, okay, now we have this reward for x and y. If you have two answers, the winning answer and the losing answer, if we compare them, kind of make a difference of them. So this is what we will get. And as you can see, when we do the cancellation or when we do the difference, we can get rid of the z of x, which is great because technically we cannot calculate the z of x. So what it says is we don't need to really understand the true value of the reward function or r of the x and y. It's just enough for us to understand the difference or comparison between two answers, the winning answer and the losing answer, and then we're good to go. So we can do whatever technically we want to do. So we can compute reward difference using only policy probabilities, which we always have. No need for a separate reward model, which we get rid of the reward model. The z of x disappears, we delete it. In this difference we have them cancelled, and this direct optimization becomes possible. Just let's quickly recap about this z of x. What is this z of x? So we covered these parts, and just remember the objective optimization. And by the way, I will put this PDF and all the material in my GitHub, and links are in the description. So optimization objective, if you remember again, we want to maximize this policy for the right answer or aligning the LLM. It's this equation, and in this equation, as you remember again, we have the reward function, we have the policy, we have the reference policy, old policy. Beta is temperature that controls exploration versus exploitation. This is a concept in reinforcement learning. If you like, you can dig into that and just do a Google search or ChatGPT search to find more about it. So this is the equation. But how we can solve it and what is the optimal policy? So optimal policy, after we solving that equation, I have the, in fact, solution of that equation right down here, which I'm not going to go into the details, but I just quickly mentioned that we can solve it with Lagrange multipliers and adding the constraint of this, that the sum of all possible answers goes to 1, and with just a bunch of derivatives we can get into the answer, which is technically as what we saw, the pi of r, or the optimal policy, is 1 over z, reference policy times exponential of the 1 over beta and reward function. But again, what this z of x is and why is it hard? Just to quickly again, let's understand it better. Why is it hard to compute? So this z of x is all possible answers that an LLM can generate for a given context S. So imagine if I say, what is the gravity? Then LLM have thousands of choices or trillions of choices, because the answers could be short, they could be long, tokens could be any choice out of the vocabulary. So just you calculate it, you tell me how many possibilities we can have. sentence of variable length, I don't know, constructed from vocabulary of maybe 50k plus tokens, so on and so forth. So that's what makes this z function, z of x, so hard to compute. So that's why we cannot directly compute this equation. So that's why we use that DPO, and that's why the name comes from, name of the DPO comes from that direct preference optimization, because we do a kind of preference. We want to see which one we prefer over which one. And again, back to that one which we saw earlier, the way that we cancel that is just, instead of calculating one reward function, we compare two of them. And when we compare two of them, we can have this z cancelled out and we get rid of it, and we have this form which is a kind of preference, we can call it, as they say, of winning and losing answer. So let's do a quick example, LLM based example for this. Imagine that the scenario is training an AI poetry assistant using DPO's implicit reward, and the prompt is write a poem about artificial intelligence. So imagine the good poem, the winner is silicon dreams awaken, algorithms dance with thought, mind meets machine at last. This is kind of creative and follows haiku structure. The current policy, the reference policy, 15% and 10%, and bad poem, let's say AI is good technology, computers are smart, the end. Whatever. The current policy is 5% chance, the reference is 8%, and when we do the DPO magic, let's say, with the temperature, the beta temperature of 0.1, we have good poem ratio, log ratio 0.4, and the bad poem is minus 0.47. And when we do the implicit reward difference, we have this number, 0.08. What's the breakthrough? What's the fun part or the good news? Without ever training a reward model, this is very important, DPO automatically knows the current policy values. The good poem, for example, what's that, 0.08 points higher than the bad poem. So this is kind of comparison between those two, and that's it, without even knowing any value function. Why? Because we just compared them together. We did not make any value function for any of them and then calculate anything else. And this is where the magic happens, where the magic comes, which makes things much easier to calculate. So also about let's quickly go to DPO loss, the final elegant formula. We have something called Bradley Terry equation. So it's all about the human preference and how human preference happens. So the probability of, winning answer to be higher than the losing answer given a context X or prompt X. The way that we calculate it is a sigmoid of the difference of their reward. And the way that we calculate it, if you just look at the what's that sigmoid function, you can easily figure out that how this equation comes to this form, that how we can get the sigmoid function of their difference. Now imagine that substituting the policy-based reward instead of these reward, what's that, the value of these, in fact, equivalent of this reward function, which as we saw was the log of the ratio. And at the very end, once we calculate everything and solved everything, the DPO loss function would be this, as you can see, which is technically the log difference of the ratios, which we put them into a sigmoid. What it says and why it is important and what this loss does is technically increases the pi of theta. The increased pi of theta is technically making winning response more likely. Technically what we saw in PPO. On the other hand, what decreased pi theta means making losing responses less likely. So that's exactly what we want. And if you have ever had the chance to have a look at DPO datasets, for example, in Hugging Face, we have 2 columns, 3 columns usually: the prompt, the answer, and the rejection. And those answer and rejections are technically winning and losing answers. Why? Because we want to increase that winning answer and teach LLM to forget about those losing functions, or giving a kind of negative value or possibility for those, probability for those kind of answers, just making them less likely to happen. And also at the same time, because we have the ratio, so it tries to stay close to the reference policy as well. And also the automatic weighting, which is focused more on examples where the model is wrong, which is okay. And why is it beautiful or useful? Let's say it's simple because just a classification loss. There is no need to calculate any kind of value function, which we had previously from RL. There is no need for RL, so which is perfect. We don't need to use another LLM, kind of critic LLM like, which makes it much more computationally expensive. It's stable, no complex RL dynamics, which is a good news. Memory efficient. We need 2 models, policy and reference, which is perfect. Theoretically grounded. As you saw, the way that we extracted that from the equations and the Bradley-Terry assumptions, it gives a confidence and accuracy that what we made is 100% correct, and it has a strong mathematical foundation behind. And it's direct. Optimize exactly what you want, the human preference. And that's exactly what we want, because we're trying to align the LLM. Why? Because we want to make it in a way that human gets the human preferred answers, and that's exactly what happens here. And there's also another example which you can have a look at it. I'm not gonna go into the details of it. And about this part, I think we don't really need this part again. If you want, you can have a look at it, and let me see if we don't need this part as well. And again, if you like, you can just navigate to this URL, and I will put it into the description. You can just navigate to it and go through it if you like to study that in more details. And about the next part now. So we had covered PPO and DPO, and how DPO is kind of comes out of the heart of PPO, and how much it simplifies PPO, because it's a preference base and it doesn't need any RL, so it's much easier to kind of calculate. But now and don't forget that what we wanted to do, we wanted to understand how DeepSeek works. So the way that DeepSeek works is none of the PPO or DPO. So what they do is something called GRPO, which is Group Relative Policy Optimization. But what it does and how it works. So as you can see here, it's an efficient RL algorithm that eliminates the need for a separate expensive critic model. Common in PPOs. We saw that we had such a problem in PPO. Instead, what it does, it normalizes reward by computing a group of different responses generated with the same prompt. So what it does is just imagine that we have a bunch of generated or possible generated answers from LLM. What it tries to do, it tries to use them, those generated answers, as a kind of population or probability population in order to decide which answer is better or worse. And how it tries to do that, when we have a group of responses, we can get the mean and standard deviation of them, and then we can decide that, okay, the new answer, how it compares with the mean of this group, and is it better or worse. So what we want to do with that probability, if it is less, if it has less acceptance rate within the group, so make it less likely. If it is better than the whole group, so make it more likely. So that's technically how it happens. So the way that it works, we're gonna go into more detail of it in a minute. We have a prompt, we have policy model pi, we have generated group of n completions, y1 up until yn, a score each completion with a reward function r, and then normalize rewards across the group, compute with advantage a of I, and then we update the policy based on that. So okay, let's see how exactly it works. So again, what was the PPO's challenge? Again, a kind of, let's say, quick recap and analogy for it. When you're training a student, imagine you need a separate teacher on the PPO. Remember, we are on the PPO. When you're training a student, you need a separate teacher to constantly evaluate how good each answer is, which is expensive, because that teacher or that LLM needs to run at each time, and that inference takes a lot of effort and computation. So PPO requires policy network, pi, theta, value network, both need training and complex interaction. Okay, now what GRPO does. So now with the same analogy, imagine what if we don't need a separate teacher. Okay, how we're gonna teach the student or train the student. Imagine what if students can learn by comparing their work with their classmates. This is technically the whole analogy and the whole idea of what's happening. The group-based learning, that's the whole concept. Generate multiple responses, like having 4 students to solve the same problem. Group-based learning, compare within the group, see who did better or worse. Learn from comparisons. I should do more like Sarah or less like Bob. And this is technically where the mean and standard deviation of all responses comes from. And then that's how we can technically compute that, okay, how we compare ourselves or each completion with the mean and the standard deviation of the whole group. No external judge needs, there is no other secondary LLM to get involved and make it, I don't know, expensive, computationally expensive for us. So the key insights again, you don't need to know absolutely absolute quality scores. You just need to know this response is better than that response. Technically kind of DPO like, because that was also kind of preference based, but this one, it has a group, so it is much stronger compared to DPO. It's faster, this way GRPO is faster, no critic joining needed, again compared to PPO, cheaper, half of the computational cost, simpler, one model, one objective, and that's it, and also effective. So let's say an example of that, what would that be? An example, a scenario and a problem, and PPO approach and GRPO's approach. So let's say the scenario is training an AI math tutor using GRPO and PPO. So the problem or the prompt is solve 3 times x plus 7 equal 22. The PPO's approach, which is complex. Policy generate response. 3x is equal 15, so x is 5. Critic evaluates. This looks like it will get reward 0.8. Actual reward is 1, correct. Update both policy and critic. Expensive computational wise. Critic learns to predict better. Policy learns from critic. Okay, that was how PPO technically works. But what GRPO does, which is a simple one, generate 4 responses simultaneously. And by the way, this group number or the cardinal of the group can change, and it depends on how many generations or completions you want to have in each of your groups. So technically, the higher the group size, the more accurate your LLM will become. And the lower that it is, imagine if it is something around 2, this technically somehow would be the same as DPO. So okay, imagine that we have a group size of 4, so we generate 4 responses. The first one is x equal to 5, the second one is again x equal to 5, x equal to 7, x equal to 3. And imagine the first one and the second one, however the answer is correct, but imagine that we have different methodology of reasoning to get there. So what it does is compares within group, what do we have, 2 correct answers and 2 wrong answers, learn directly, do more like the correct ones and don't do like the wrong ones. And as you can see, there is no need for critic or calculating any reward function. So the result, GPO achieves similar learning with half of the complexity and computational cost, which is perfect. And that's why the guys in DeepSeek, they managed to make it that much efficient with, I think it was something around $5 million. They managed to make something as good as something like GPT-4o and so on and so forth. So yeah, step 1, again, going into a little bit, diving into more details. The goal, generate G different responses that explore various approaches to the same problem. We have output 1 up until output G, and we sample them all from this policy, given the context or question or prompt of X. X is the prompt, O of I is the I've generated response, G is the size of the group, typically something around 4 to 8, and pi is the current policy. Diversity technique, what that diversity technique means, temperature sampling T is higher than 1, which means technically, as you know, it's the temperature in LLMs, which gives more creativity, top K sampling, and also multiple random seeds to make sure that we have good coverage of the diversity and a better population in terms of probability and statistics. Why this diversity matters? Exploration, comparison, robustness, and signal strength. Just the ones that we have in foundational statistics and probability. Group size trade-off, again, smaller groups, fast but limited comparison, as I mentioned, medium ones, good balance. Large size, it's gonna be really good and strong, but it's more expensive. And also there is again another example here with the group size of 4, and you can have a look at it. It's again another example, LLM based example. You can have a look at it and see how it works. I'm not gonna explain it here. And I think this part is also not needed really. Yeah, and this one is just simply the way that we calculate that advantage and the kind of the kind of advantage that we're going to give based on the performance of each element or each output within a group, which is technically the heart of GRPO. What it does is transforms raw reward into learning singles by normalizing within each group. And so what we have is just group mean and the standard deviation, and the advantage would be just how each of those outputs did compared to the mean and standard deviation of the whole group. So if advantage is bigger than 0, response is better than group average. If it's equal, response is exactly average of the group. If it's less, so the response is worse than the average group, so make it less likely. In this case, make it more likely. And epsilon is just make sure that we don't have any kind of division by 0. And again, yeah, there is also another numerical or LLM based example which you can again go through it, which I'm not gonna go through it here because of the sake of time, to save some time. And let me see if I can see. Yeah, let's just quickly go to this equation as well. So this is technically the heart of the GRPO loss and what it exists in the DeepSeek and GRPO's paper. It combines the PPO styles clipping also, because remember that we had that clipping, and that clipping was really important because when we want to, and if you remember, we don't want to do a sudden steering wheel turn because it might make the LLM forget everything. So what we want to do is we want to make sure that, okay, we're not gonna get into too much complexity and computation by calculating the reward function. That's why we're generating outputs, different outputs, and then we calculate the mean and standard deviation of the group. And once we update the policy, what we're trying to do is, if the policy or if the update is too high, we don't want to go too high within a direction. We just want to clip it. And why is it important generally? This is kind of analogy for it. Imagine that, okay, this is the optimal policies on top of this hill or whatever the mountain is, and these are the small updates that we want to make. But the thing is, imagine one update of the policy is too big that if we want to go within that direction, within the gradient surface of the optimization problem, if we go that big in that direction, we're gonna fall off the surface of the optimization, and it would make our optimization, to solve our optimization problem, much harder. So we wanted to make sure that we're not gonna take very long steps. We want to have the updates to make sure that we learned something, but we want to make them short in order to make sure that our LLM is not gonna forget what it was doing. So again, we have that G, which is a group size, and the rest of the thing, if you remember from the PPO, is technically the same as PPO. We have those RIs, which are the ratios, important sampling ratios, and the advantages, just like that we calculated previously. And also what we do is we do the clipping, and this clipping is again just because we don't want to make huge updates. And also at the same time, in GRPO loss function for DeepSeek, we do encounter the callback lib difference in order to make sure that the update of our LLM or the probability of that would match and would stay within a certain distance from the reference policy, because again, we don't want to make it too much difference. And yes, the KL penalty is just to stay close to the preference policy. Positive advantage is increase the probability of generating OI. Negative is just decrease the probability of generating a response, a specific response. Clipping is just preventing too large policy updates. And KL penalty again is maintains the coherent language generation. The differences again with PPO, no critic network, which means computationally it's much better. Batch-based learning or group-based learning, because we have groups. And relative rewards focus on better than peers, not absolutely good, which is somehow the same concept as DPO. Simpler pipeline, one model, one objective, and that's it, which makes it much easier to calculate and solve the whole problem. And let me see if there is anything else. No, we don't want this one as well. And yeah, so that's technically it. That how we calculating the and what this GRPO technically means, and how they did trained DeepSeek with this method. In the next section, what I'm trying to do is I'm gonna walk you through the code of the taking one reference model like the one that they did in DeepSeek R1. So what they did was they took DeepSeek V3 and they tried to use this GRPO on top of it to make it aligned and much stronger. So what I will do is I will take a small simple model, something like Quen or Gemma 1B, something like that, a small model, and we're gonna try to teach it how to reason and also how to make sure that we can align it. For example, how to make those reasoning steps, how many reasoning steps that it can have, how to make sure that the answers are long or short enough, or they are not going to be, for example, what's that, too long or too boring, and so on and so forth, with this exact same method that they use for this GRPO objective function. So yeah, that's the next step. Okay, now in this last section, I'm gonna walk you through the code and how we can generate something like DeepSeek R1 out of a base models, something like DeepSeek V3. So the thing is, I'm not gonna exactly do it with DeepSeek V3 or R1. So what I'm trying to do here is just give an example of how this is possible and how the whole pipeline works. So it's a kind of demonstration of how the whole pipeline just works, and that's it. So yeah, we can start it from here. And by the way, if you want to see the full code, you can find it on my GitHub. The full code is technically 90% copy of this guy, which I put it on the references. You can have a look at his GitHub as well. He has some really nice tutorials and I can say different LLM models. And yeah, so this code is this Jupyter notebook is available via Colab and my GitHub, so which I put the link into descriptions. So let's quickly look at it, how it is possible and how we can just make and give reasoning ability to a base model. So what we're trying here to do is, as our base model, we try to use Qwen 2.5 with 500 million parameters. Technically it is about 494 million parameters, which technically acts as DeepSeek V3 original model. And what we're trying here to do is to give reasoning capabilities into this model. So how this is possible? So the way that we're trying to do is, in fact, we have a bunch of, I can say, reward functions, which we can see it here, prompt template design, and a bunch of reward functions in which we try to teach the LLM to behave within a certain framework and do not generate or, I don't know, give answers in any other way. So we need to design a couple of reward functions and then give them into a GRPO function, GRPO trainer from Hugging Face, which we can see it technically here in the TRL package, which is I think transformer reinforcement learning, something like that. As you can see, we have the GRPO trainer and we have PPO trainer, so we just import them all. And also what we're trying to do here is we're trying to do the reasoning over a data set of math problems. So what we need to do is we need to validate if the generated responses are valid, and usually the models and LLMs try to generate it in LaTeX format. So we import these functions in order to make sure that we can parse the LaTeX output and make sure that, for example, if the answer is 1/2, even if it is 2/4, so they are technically mathematically the same. So these two libraries and functions would validate the output. And as I said, TRL is for reinforcement learning tasks, GRPO and PPO, and also the transformers. We import a bunch of other imports in order to load our Qwen model. And also this is the training data set. These are the training data sets, and these are just a bunch of mathematical and coding challenges and problems which we're using them here. And as you can see, the output shape is problem, solution, and the message. And usually message is combination of problem and solution in one big JSON. And here what we do is just simply we import, we add the model name from a Hugging Face and we load the model and we are ready to go. So technically, as I said, we are trying to give this model the capability of reasoning, how to reason, how to be able to reason. So the system prompt would be, in fact, we're trying to give it directions that how it should think and how it should answer. The assistant first thinks about the reasoning process in the mind and then provides the user with the answer. The reasoning process and answer are enclosed within think and answer tags, respectively. So this is the system prompt, and just in a minute we will find out that how we can put a reward function to make sure that the model will behave within this manner. So now to the section of multidimensional reward system. So the first and the foremost thing is, because we have math problems and coding challenges, we need to make sure that the output will be parsed, and we can make sure that the output of the LLM and the grand truth will be parsed in the right way. So the way that it works is, if the answer and the solutions are correct, they are the same thing, give a reward of 1. If they are not, so just don't give any reward. And if the parsing of the latex or math problem failed, just give half as a reward, so which makes sense and makes it fair, because we failed doing the parsing, so we're not sure that the LLM was right or not. So for example, imagine the problem is, what is 2 plus 3 times 4? The grand truth is 14. The model response would be in the think and answer in fact tags. The verification process would be parse grand truth 14 into its symbolic representation, extract model answer is 14, again symbolic representation, and mathematically they are the same. So it is true, as we saw here, and we will give a reward of 1. Or if it was, for example, the model response was 20, the symbolic representation is again 20, and the grand truth was 14, and mathematically speaking, they are not, when we parse them, they are not the same or equal, so the reward would be 0. So this is one reward function in order to make sure that the answer provided is correct. The next reward function is specifically for formatting compliance, just to check if the formatting is correct. So as we saw earlier right here, we want the model to first reason and put the reasoning and reasoning steps into think tag, and then provide the answer in the answer tags. So the way that reward function for this works is, technically we can do it simply. There are definitely other ways of doing reasoning, but this one is very simple and we want to keep it simple. So we just use regex in order to find the think and answer tags to make sure that model behaved in the right format. So the correct format with the reward of 1 would be something like this. In the think tags we have, I need to solve 2 plus 3 times 4. Order of operations says multiply first, then addition. This was in the think process and tag, and the answer is 14, which is exactly what we want. But if the, for example, in a case of incorrect answer, it can say the answer is 14 and there are no tags, and we don't want something like that because we want the reasoning. So that would be reward of 0. This is the second reward function. Now the next reward function, which in this reward function, as we saw that in reasoning, we want to have more reasoning steps. We want the model to make it clear that, okay, what are the steps of the reasoning and do they make sense or not? So that's why we can technically say the more reasoning steps that we have, somehow we can make sure that, okay, the reasoning steps are better, are more aligned, and they make sense. So for example, we can say, okay, I want at least 3 reasoning steps. So the way that it works, the way that we can define reward function for this is we can count reasoning indicators, which I go in a minute, explain what are they in a minute, and divide them by 3, and then choose the minimum of 1 and whatever that the result of this count is. So what are the indicators? Indicators are some of the things like first, second, next, finally, which kind of represents the reasoning steps for us. So if we have 0 indicator, the reward would be 0, because technically there wasn't any reasoning step. If there is 1, the reward would be 0.33. 2 would be 67, and 3 plus indicators, which we technically is our ideal, is the reward would be 1. So high reward example with a score of 1 would be in the think tag. We have step 1, identify the operation orders. Step 2, calculate multiplication first. Step 3, add the remaining term. And then finally, verify the result makes sense. This would be exactly what we want. The best, in fact, answer that we can have. So indicators are step 1, step 2, step 3. Finally, for indicators, we have the reward would be the minimum of 1 and 4 over 3, which is 1. An example for low reward example would be with a score of 0.33 would be in the think tag. We have just multiply, then add to get 14, which is not really informative. And this is another reward function in order to make sure that the reasoning steps are logical and they make sense and they have enough lengths, or as we had it here, indicators. The other one would be the length of the response, which is also very important, because what is really important when LLMs want to, in fact, answer a question is we don't want very lengthy answers, and also at the same time we don't want very short answers. So the way that we calculate this reward function is we get the length of the response and we divide it by max length, which is a kind of parameter that we can choose to whatever we want it to be. And then we do a cosine factor, which we get the cosine of that progress times pi, and then we do this calculation. And what this technically this calculation and equation mean is correct answer and a short answer. Correct short answer has a high reward. Incorrect answer but long would have less penalty. Why? Because at least it tried. But incorrect short answer would have the highest penalty because it didn't even give it a try, which we don't even like it. And also if it is a right answer but very long, it's acceptable, but it has less reward because it's not very concise. So the best one would be to the point and concise, which is correct answer but also somehow short. So if we say max length, an example for that, if we say max length is 1000, and if we say correct range is something around between 0.8 and 1, and incorrect is minus 0.5 to minus 0.1, the correct answer example would be something like a short response, something like 100 characters, the progress would be 0.1, cosine of that would be 95, the reward would be 99, because we have short and correct answer. And in the case of incorrect answer, with again in fact what's that, incorrect but short, the reward would be minus 0.12. And on the other side, if we have incorrect and long, it has minus 0.46. So this is technically what and how the reward function works in terms of length. So what we had so far, we had reward function for length, we had reward function in fact for reasoning steps, how many reasoning steps that we can have. We had we had reward function for making sure that the reasoning tags are in the right format and in the right way, and also another reasoning reward function for calculating and parsing the right answer. So all these reward functions technically will be given to the model, and make sure that model will be trained with based on all these reward functions with GRPO method. And also there is another reward function as well, which tries to make sure that there aren't that many repetitive words in our response. So the way that it works is simply we can calculate it with n-grams diversity measurement. And the way that it works is we have unique, imagine that we have 3 grams or 4 grams. We have unique n-grams and total of the n-grams. And with this, within this way, we can find that, okay, how many times we had repetitive words. And if we have too many repetitions, so technically that would, if we have high repetition, that would give a large penalty. If it is more diverse language, it would give a smaller penalty. And yeah, and this is also an example for that, which you can go and have a look at it. So technically what happens after all these, and if I want to explain just quickly again in the code, so these are technically, you can just go and have a look at it. This is the code for each of those reward functions. It's not hard at all. It's just turning all those explanation into code. And the last step for that, which is the technically, I would say here, I think this is repetition, and then yeah, here is the training arguments, which we can literally put how many steps we want it to be trained, number of training epochs, and I don't know, number of batch size per device, the weight decay, warm-up ratio, so on and so forth. In the next section we have a data class, which in this data class we configure the model, a bunch of model parameters like model name, I don't know, v-type, trust remote code, and attention implementation, which we use flash attention to. We set up the arguments, and also we set up the GRPO script arguments. And here we just get the reward function. We define the general reward function, which is technically a set of all functions that we explained earlier. And then just remember this name, get reward functions. We have all those reward functions all here. As you can see, repetition, penalty, cosine, reasoning steps, format, accuracy, so on and so forth. And then what we do technically is on the GRPO config and GRPO trainer, what we do is we give the model, we give the reward functions and GRPO config and just a bunch of configs, and training and test and evaluation dataset. And then simply we can start the training, and the model, which in this case was Quen 500 million parameters, will be trained in a way that it will make sure that it has all these guidelines, all these, I can say, frameworks, and it will follow all these. So by these reward functions and GRPO, we will give it the ability to reason. Why? Because this reward function works in that way. And this is the whole thing. And this is technically how they made DeepSeek R1, which has the reasoning ability, out of DeepSeek V3. And yeah, feel free to go to the code and go to this Jupyter notebook, which is available on Colab. Try to run it and see if you can understand all the steps, and feel free to ask any questions on the comments sections or on the GitHub or wherever you like. And yeah, that's it technically for this DeepSeek R1 section. Thank you.